Okay, I'm going to go ahead and go through this test here. Of course, the first page is just some matching and 10 scenarios. So on number 1, are there any differences in average? So we're looking at average as a quantitative variable in means for students who took one of 3. So there's 3 groups there. And so that's going to be an analysis of variance or option G. The next one, is there a relationship? That's a pretty good clue right there that we're going to be looking at a chi-square. If it was a linear relationship, it would be H. But let's go ahead and make sure we're looking at where they do their most shopping. And they've got 4 stores there. So that's a qualitative variable with more than 2 categories, or it's multinomial. And the same with the other ones. With income level, we just put them into 3 categories. In this case, both of those are multinomial, but as soon as you have one multinomial, 2 qualitative variables, at least one of which is multinomial, that is a chi-square test. Looks like I've got an extra word in there. Okay, so is there a difference between the proportion of Arkansas residents with college degrees and the proportion of Texas residents with college degrees? So we're looking at proportions, and there's 2 groups. The groups are Arkansas residents and Texas residents. So with 2 proportions and 2 groups, we are looking at a 2-proportion z-test. Number 4, we're looking at the time it takes to complete the task is decrease after a new program, and we've measured before and after, so that is a matched pairs t-test. The same people take the test at the beginning and the end. Is the proportion, could have said percentage, but proportion less than a specific value, that's a 1 proportion z-test, or D. Is there a relationship? And we have a multinomial qualitative variable there, and whether or not they favor. This one is binomial, but you only need one of them to be multinomial for this to be a chi-square. It has 2 qualitative variables. One of them gets into categories freshman, sophomore, junior, senior, and the other category is they either do or do not favor switching from semester to quarter system. Number 7 is the average time. It's a quantitative variable, and we're looking at the average of that to complete the test over 80 minutes. So we're comparing to a specific value, and that is A. 8, is there a linear relationship between exam scores and the number of hours a student works? But as soon as you saw the linear, that's a simple linear regression. Okay, difference in percentage. So since it's percentage, we're looking at proportions of business majors who can speak more than 1 language and the percentage or proportion of engineering majors. That's 2 groups there, business and engineering majors. And we're asking each, or want to know about each, whether or not they can speak more than 1 language. That is a 2-proportion z-test, or E. Does medication lower the average level of stress? And I think, if it's not on there on the one you have already, I thought I had reposted this. You can answer it the way it is, but what I thought it would be better if I said, does medication lower the average level of stress more than it does if you have an exercise program? See, we have one group of people that participate in a meditation program, and then another 100, a separate group, who participate in the exercise program. So we have 2 separate groups, and we're looking at averages or the difference in means for those 2 groups. That is option C. anyway, on this problem, and I'm going to do a little bit more than is called for on this particular problem here, you should recognize this as an ANOVA. There are 3 training methods, and we're looking at the impact of these training methods on average productivity. And it's asking you to do the p-value approach, and then based on that, and I think also there was which specific means differ. Actually, I'm going to use my calculator and just put these numbers into my calculator into lists 1, 2, and 3. And give me a second here. I had done that earlier, but I'm going to go ahead and work it the way it says here, and then I'm going to come back and do a little bit more. So what I'm doing is I'm putting all of the numbers into lists 1, 2, and 3. And then after I've done that, I'm hitting stat, tests, arrow up 1 to ANOVA, second L1, comma, second L2, comma, second L3. And then sorry about that. The wrong paper there for a second. Anyway, I've got that there. So I'm going to come back here and say, what were the hypotheses in HR? And the hypotheses are for research hypothesis, at least one of the following is true. Mu A not equal to mu B. Mu A not equal to mu C. Or mu B not equal to mu C. Now, there's at least one difference between population means. That's the research hypothesis. HO was that all 3 population means are the same. At least we won't. Yeah, that they're all 3 population means are the same. So using the calculator to get a p-value, if you run the test there, you would see about 3.16 times 10 to the minus 4. It just says really 3.16287 That E means exponent to the minus 4, which is the same thing as 3 zeros, then 3.16 there. That's the p-value. And with alpha 05, part C is we would reject HO if the p-value is less than 0.05. P-value is equal to 0.00036. That is less than 0.05. Therefore, you reject HO. So we could state that just like we've done p-values in the past. And we would say if there is no effect, or in this case, if HO is true, that's always the same thing. If there's no effect, if HO is true, if mu A is equal to mu B is equal to mu C, then, just like always, if then for a p-value, there is a very low chance, and I almost said an infinitesimally low chance, but then I decided to go with a very low chance, which was 0.00036, and that is pretty low, of obtaining sample means this far apart. And I don't have the sample means yet. We will in a minute. But it would be the sample means x bar A, x bar B, and x bar C. Okay, there's a part D here. I'm going to work that along with the rest of the problem that isn't up here right now. But I'm going to pause here and just change this a little bit. Okay, I just want to go on. I know the problem as I originally wrote it didn't ask you to work everything by hand, but you need to be able to do that. So what I've done here is just rewrite the hypotheses. I switched the order of HO and HR, but that doesn't make any difference. HR still, at least one of the following is true. We already had that on the other sheet. And I went ahead here and just wrote down, we're going to compute the mean and variance for method C. That'll make sure that you can recall how to do that, but I just went ahead and as a given right now wrote those down here. So I'm just going to kind of go through here. This would be reject HO if F test is greater than some value. So we'll need to get degrees of freedom, and for the F test, for the ANOVA, the degrees of freedom for the numerator is k minus 1. That's 3 minus 1 is 2. Remember, the k is just the number of groups, 1, 2, 3. And then the degrees of freedom for the denominator is equal to the total sample size minus k, where the total sample size is 1, 2, 3, 4, 5, 6 times 3, because there's 3 groups there. So it's just the total sample size of 18 minus 3, and that's going to be 15. So then we can look up in the F table for 2 and 15 degrees of freedom. I know where that's going to be, but I'm going to look anyway. That's 3.7. I'm just going to write up here that I think I'll leave that there. Okay, so then we know we're going to compute the F test, and the F test is equal to the mean square treatment divided by the mean square error. So we're going to compute the mean square treatment and the mean square error. And to do that, a couple things we need to do first. First of all, we're going to compute the mean for mean and variance for group C, and the sum of those numbers there is 72. And so x bar C is going to equal the sum of the x's divided by n, which is 72 divided by 6, and that's 12. And then we have to subtract that mean, that 12, from each of the values here. And then we have to square those deviations. And that's going to be 22. And so the variance for the C's is this, the sum of those squared deviations divided by n minus 1, which is 22 divided by 5, and that should be 4.4. So I'm going to get the MSE first. It doesn't take up that much calculation. The MSE, hold on a second. Okay, so the mean square error is equal to the average of the 3 variances. Just add those variances and add by k, which is the number of variances you have, the number of groups. So we have 2.4 plus 4.4 plus 4.4 divided by 3. And that is 0.5. 3.73. So that gives us the bottom of this. Okay, so for the MSTR, I'm going to start. I know I need to get the mean of the means, or the grand mean. That's just x bar A plus x bar B plus x bar C divided by k. And so that's equal to 6 plus 9 plus 12 divided by 3, and that's going to be 9. So the mean square treatment is going to equal NA, the size of group A, times x bar A, the mean of group A, minus the overall mean squared. What we're actually doing here is for each of the 3 sample means, just how far apart are they, except for we're getting that by the distance from the mean of the means for each one of them. So MB, x bar B, minus x bar squared, and then the same thing for group C. And if you had 4 or 5 groups or whatever, you would just continue with that progression right there. And that's divided by k minus 1. And so that's going to equal the size of the first group, 6. 6 minus 9 squared plus 6. 9 minus 9 squared plus 6. 12 minus 9 squared. And all that's going to be divided by 2. Let's see, that ought to be, I'm going to say 54, that's right. So now we have our MSTR, and subtracting or dividing that all out, let's see, 54 divided by 3.73, that's going to be 14.48 about. And that is greater than 3.7, so you reject HO and conclude that at least one of those is true. That's really what I call part A of the problem. We're just doing the hypothesis just to ask the question, is there at least one difference between population means, or could all 3 population means be the same? We've rejected that HO, that they're all the same, so we conclude that there's at least one difference between means there. So now the question is, which one or more of those means differs from the others? And so there's 2 things I'm going to calculate to answer that, and let's see if I can fit this over here. The first thing I'm going to do is I'm going to get the absolute value of the difference between each pair of means. And I'm doing it up here just so it's right next to the corresponding population means. We'll see if I have room for that or not. So I'm going to have 6 minus 9, and that's going to be absolute value is 3. And between A and C, I've got 6 minus 12. The absolute value there is 6. And then for B and C, this 9 minus 12, and the absolute value is 3. So that's really the information we have about difference between means, is just the difference between the sample means for each pair of means. So A and B, A and C, B and C. So these are the actual differences between pairs of sample means. So now the next question, or I hope what a logical question would be is that, okay, so how far do a specific pair of sample means have to differ before we can conclude that the corresponding population means are different? And so to do that, down here, I'm going to compute the HSD, honestly significant difference test. This is Tukey's HSD. This is one of many tests that you might use here. But anyway, it's equal to Q, which is a number we're going to look up in the table, times the square root of MSE over group size, which is the same thing as NA, NB, and NC. It's just the size of each group, or 6. So that's equal to, I'm going to leave space for Q there. MSE we had calculated a minute ago to be 3.73. The group size was 6. Now we need degrees of freedom here for Q. Just add over here. The degrees of freedom in the numerator is equal to K, which is 3. The degrees of freedom in the denominator is the same, and we had that on the previous page, is the same as it would be for ANOVA. So different in the numerator, same in the denominator. But I'll go ahead and write that down here. It's the total sample size minus K, or 18, because there were 18 total values in our sample, 6 in each of 3 groups, minus 3 is 15. So now in the Q table, which is the back table on the tables that I've given you when you took the last test or in class or whenever I gave them to you. So anyway, 3 and 15, you should see the number 3.67. So that's our Q. And if you multiply all of that out, I got 2.89. So any difference between sample means that's larger than 2.89 would reflect also a difference between corresponding population means. And so 3 is greater than 2.89, 6 is greater than 2.89, 3 is greater than 2.89. So you can say all of those, all are true. In this particular case, they are all true. Now the other thing you can do here is you can then just kind of look back at the sample means that you have and everything, and we had means of 6, 9, and 12, and since they all not only differ between sample means, but they're all different between population means, we can just look and see which one of these was the largest. And the largest mean we got was for training method C. And so if I were using this, the data from here to make a recommendation, I would recommend that all other things equal, that you use method C. And the only reason I'm doing that is because all of them are different. And so I'm just going to go look for in this case, the highest mean and say that's the highest population mean as well. Okay, on to the next problem. Okay, so first of all, let me note, I think this will be right for hopefully anybody that's listening to this. If you're listening to it at exactly the wrong time, I did change the standard deviations on this problem, so that was 18.9 and 12.9. Anyway, I did it for, let's just say I changed it. So anyway, we have 2 samples, one of Kmart customers and one of Walmart customers. And over here on the left, I've gone ahead and summarized that we have samples of 30 from each, with sample means of 36.4 and 31.2 for the 2 groups, and sample standard deviations of 18.9 and 12.9. And then I went ahead and computed the 2 variances here, 357.2 and 166.4. You might note that those are pretty far apart from one another. Okay, so anyway, we want to know if we can conclude that the population mean is higher for Kmart customers for Group A than for Group B. And, of course, HO will be that the two population means are the same. And it says to use your calculator to get the p-value. So I'm going to do that. Stat test, 2-sample t-test, and then just enter in the means. The mean 36.4, standard deviation 18.9. That's out of 30. Select greater than. No, we're not going to pool. And calculate. So the p-value is 0.109. And we would reject HO if the p-value was less than 0.05, and 0.109 is not less than 0.05. So you fail to reject HO. Mu A could equal mu B. Our evidence in our sample is not so great. It's not strong enough that we can reject HO and conclude that the population mean age is higher at Kmart than it is at Walmart. Okay, so while I'm here too, I'm going to go ahead and do this with the critical value approach and work it out by hand. And the critical value approach, now I'm going to say on our calculator, it said the degrees of freedom were 51.2. We're just going to round that down. We'll always round those down. So the degrees of freedom is 51. So let's see. I'm going to work down here now. Okay. This is the critical value approach. And so I'm going to reject HO if t-test is greater than some value. So on our t-table, this is a one-tailed test, and alpha is 0.5, and we have 51 degrees of freedom, so that's 1.675. We had our degrees of freedom right here. Since the hypothesis was greater than, that's one-tailed test, and we've got our alpha 0.5 up here, so that's where I got the 1.675 from. And so the t-test is equal to the statistic, the difference between the two sample means, minus the hypothesized difference. This is what's hypothesized in the null hypothesis, divided by the standard error, where the standard error is going to be the variance of group A divided by NA plus the variance in group B divided by NB. That was supposed to be a squared up there. So the difference between our sample means is 36.4 minus 31.2 minus the hypothesized difference, which is 0. See, up here our HO was mu A equal to mu B. If that's true, then mu A minus mu B is equal to 0. Same thing. Divided by the square root of 357.2. Of course, you could just put 18.9 squared right there if you wanted. Divided by 30. Plus the variance of group B, that's 166.4, divided by 30. That should, when I did on the calculator, it came out to be about 1.244, but I'm going to go ahead and calculate it this way and see if I had any. It's probably going to be a little different just due to rounding, but I just want to check myself. fact, that's what I get is 1.244. 124, I'm going to put that, which is not greater than 1.645. So again, I fail to reject HO and conclude that mu A could equal mu B. While I'm here, I might as well do a confidence interval as well. So I'm going to do, in this case, a 90% confidence interval. Mark some of this off here. So it's going to be, maybe I can work it over here, x bar A minus x bar B. That's the statistic, which we know is going to be whatever 36.4 minus 31.2 is. Let me go ahead and put that as one number. 36.4, 31.2, that's 5.2. So it's going to be 5.2 plus or minus. And so we're going to have a t-value, which for 90% is going to be 1.675 times the standard error. And the standard error is that S squared A over NA plus S squared B over NB. And so that's 357.2 over 30 plus 166.4 over 30. And so I get 5.2 plus or minus basically 7. Checking here, I'm going to check this about. So I'd get that by subtracting and adding to be about minus 1.8 to about 12.2. And now what I'm going to do, one more check here, I'm going to do stat test, 2 sample t interval. All the numbers should be in there. Make sure it says 90. And I get about minus 1.8 to 12.2. I get minus 1.798 to 12.198, which I did do a little bit of rounding right here. Okay. Okay, in this problem we have a linear relationship and we have a variable x and y here. And it says to use your calculator, get the test statistic and all of that. Actually, I think we'll do that in a minute, but I'm just going to go ahead and calculate everything as if we weren't using our calculator. In other words, I'm going to have to calculate the means, the standard deviations, the cross products, and the covariance, and the correlation. So I'm going to do that first. And then as we get down and check figures and everything, we'll use the calculator when we get there. Well, first of all, okay. Try this again. So, what I was about to say was the sum of these numbers is 102. And the sum of these numbers is 300. So I'm going to keep over here, x bar is the sum of the x's divided by n, which is 102 divided by 6, and that is 17. And y bar is equal to the sum of the y's divided by n, which is 300 divided by 6, which is 50. So the next thing I'm going to do is I'm going to get the deviations for x. So I'm subtracting 17 from each number here. 0, 9, minus 2, minus 8, 5, and minus 4. Okay. And I'm going to do the deviations for y as well. And I get 4, 20, minus 10, minus 20, 18, and minus 12. And then I'm going to get the cross products, leaving some space there to get the squares in a minute. And so 0 times 4 is 0. Just multiply across here. And then I've got 180. That's the 9 times 20. And then I've got 20, 160, 90, and 48. That's a 20 there. Kind of like a 7. But anyway, the sum of that's 498. And so to get the covariance of x and y, I'm going to get the sum of those cross products divided by n minus 1. That's equal to 498 divided by 5, and that is 99.6. Then I'm going to go ahead and get the squared deviations. And so and of course getting those sums. That's 190. So the standard deviation for the x's is equal to the square root of the sum of the squared deviations divided by n minus 1. And so that's equal to the square root of 190 divided by 5. And that's 6.16. And then the standard deviation of the y's, sum of the squared deviations, this time y sub I minus y bar squared over n minus 1. And that's equal to square root of 1384 divided by 5. That's equal to 16.64. And then using that information here, we've got the covariance and the two standard deviations. I'm going to come over here and compute R, which is equal to the covariance of xy divided by the product of the two standard deviations. So it's that 99.6 divided by 6.16 times 16.64. And that all comes out to be 0.971. So that's R. Now I'm going to come over and work on the rest of this problem here a little bit. Part A said to write the hypothesis, and basically, we're just looking right up at the question here. HR is that there is a linear relationship between hours of training and productivity. And another way that you could say that is that the population correlation coefficient is not equal to 0. 0 would be no relationship. and though we won't deal with it as much in here, you could also say that the population slope is not equal to 0. Because if the slope is 0, you just have a straight line, horizontal line. HO is the same thing except for not. There's not a linear relationship between hours in training and productivity. The correlation, population correlation coefficient is equal to 0. The slope is equal to 0. When you work your calculator, that's what you're going to see as the symbolic notation there. I'm going to use the calculator in a second, but before I do, let's compute the t-test given the other stuff that we have here. T-test is going to equal the statistic minus the hypothesized parameter, the sample correlation minus the hypothesized, or what's hypothesized in HR, divided by standard error, which is 1 minus r squared, divided by n minus 2. So our correlation was 0.971. We're just going to subtract the 0, which was in HO. That's divided by 1 minus 0.971 squared. I'm going to put a parenthesis all the way around that, and then put n minus 2, which is 4. And that's going to come out to be, let me calculate, see what it comes out to be. Now what I'm doing is I put 0.971 divided by square root, and that opens one parenthesis, open another one, and you can put 1 minus 0.971 squared, then close one parenthesis, then close the second parenthesis. I'm sorry, before you close that one, divided by 4, and then close the second parenthesis. You should get about 8.12. I'm going to verify that with my calculator now. So I'm going to dang it. I'm going to put the numbers from the problem in. So I'm going to one of my lists, and I'm putting 17, 26, 15, 9, 22, 13. So I'm just putting those in my calculator and a list in my calculator. I tend to put mine X in list 4 and Y in list 5. I usually use those first three groups for either the match pairs test or for the ANOVA problems. But anyway, you can put them wherever you want. And then in the next one, for me, L5, I'm putting 54, 70, 40, 30, 68, and 38. And once I have all of those in, stat, test, down to the bottom, the linear regression t-test, and it should be not equal to 0 on the hypothesis, and I calculate that out, and with my calculator, I got 8.14, and I'm going to write that difference off to just rounding error. In fact, I'm pretty confident that it is just rounding error. So anyway, that's the t-test value. You can either, well, in this case, it said to get it from your calculator, but you should also be able to get that using this formula. So the next part is, should the null hypothesis be rejected? And so we reject HO if t-test is greater than some point or less than minus. I'm just going to tell you, I'm not going to ask for much of an explanation on the critical value. We're just saying when we get this far away, this many standard errors or further away, we're going to reject HO. It's actually not a bad way to put the explanation there. But anyway, with a two-tailed test and 4 degrees of freedom, that's going to be 2.776. And whichever way you calculate it, at 8.12 or 8.4, those are greater than 2.76. So we reject HO, and we conclude that there is a linear that the population slope and the population correlation are not equal to 0, whichever way you were to test that. Okay, I think, I'm just going to go ahead and put this last part on there. On part D, it says if there is a linear relationship, which there is, we have concluded that. Write the equation that describes your line. And remember, the general equation is y hat is equal to a plus b x. The hat meaning that we're forecasting or predicting. The a is the y-intercept. The b is the slope. So in our case, we're trying to predict productivity. I'm putting a hat on it to say we're predicting, is equal to A. Now this I am going to get from my calculator. A was 5.44, and then the B was 2.62 times hours of training. Now let me tell you, there's another thing that I didn't ask on this one, but could have and probably should have. Let's say now that we want to get some actual forecasts for different hours of training. I'm going to warn you right away, so our training goes between 9 and 26, and so we should only be making forecasts within that range of data. So if we want to predict for 20 hours of training, you can just plug 20 into that equation, and you would get 5.44 plus 2.62 times 20. And so if you did it for 20, that would be a forecast of 57.84. I'm just making this number up right now. But if I asked you to do it for 50 hours of training, you wouldn't just plug that in because the highest hours of training you have is 26. So you would say that that is out of the range of X that we have in this problem. Therefore, you should not use this model to forecast. This is different. Okay, on problem 4, hopefully it took you about that long to figure out this was a matched pairs t-test. And I am going to first of all just do this with the calculator, and I am going to go through and do something a little more lengthy here. But to do this on your calculator, hit Stat and Edit, and in lists 1 and 2, put the numbers that you have here for after and before. And verify that you have the right numbers in there before you get any further. Okay, I've done that. So now go up and highlight the L3 on list 3 and hit second L1 minus second L2. I'm going to do after minus before. And you should have a column of numbers now, 7 minus 1, 4 minus 7, 10, and 5. Of course, the first number is 28 minus 21 is 7, and so on. In fact, I'm going to go ahead and write those numbers down here just for subsequent later use here. 7 minus 1, 4 minus 7, 10, and 5. those are just the differences. Those are now your x's. Or if you want to call them d's, that's fine too. Just need differences. So to do the 95% confidence one, I'm just going to do stat tests. It's a simple t interval, option A, and select data and list 3, and we're doing a 95% confidence interval and calculate. And I got minus 3.401 to 9.40. I should have just put 3.40, but actually got 9.4007. I guess I should put the whole thing there to give me a chance to say 007, you know. Oh well. So anyway, based on that interval, can we be confident that the training is effective? No. The interval includes 0. Okay, so now let's say we were going to do this by hand. The confidence interval would be the sample mean plus or minus 2 times the standard error, which is s divided by the square root of n. So to get the sample mean, we're going to add these numbers up and divide by the sample size. And I get the sum of those numbers to be 18. So x bar is equal to the sum of the x's divided by n, or 18 minus, divided by 6 is 3. And then I'm going to get the deviations. And so x sub I minus x bar is 4 minus 4, 1 minus 10, 7, and 2. Then I'm going to square all of those. 16, 16, 1, 100, 49, and 4. And then I'm going to add all of those up. I get 186. Okay, and so the sample standard deviation is equal to the square root of the sum of the squared deviations divided by n minus 1, or the square root of 186 divided by 5. Is about 6.099. If you rounded that to 6.1, that would be okay. So anyway, over here we have 3 plus or minus, we're going to get a t-value in a minute, times s, 6.099, divided by the square root of n, which is 6. And so now to go over and get the t-value, you have a 95% confidence, and this is at 5 degrees of freedom. That should be 2.571. And so let me just go ahead and do some calculating here. I got minus 0.3401, maybe a little bit more, but 3402 actually, if I did rounding like I normally would. And then I'm going to add, and I get 9.40. So in fact, that verifies my calculation that I had up here with the calculator. While I'm here, you could have said here 3 plus or minus, and then just get the other side of that. And let me calculate that real quickly here. And I would have gotten 6.4015. There's some more there, but that's 6.40 would have been sufficient. I'm not going to work it out right now. I guess I can. Let's say this were a hypothesis test. Our research hypothesis would have been mu greater than 0 and HO mu equal to 0. We would reject HO if t-test is greater than, and I'm going to say alpha 05 here. Okay, that's going to give us a different number than we have over here because I used a 95% confidence interval, but let's do that anyway. Let's say we have an alpha of 05. Now, it's a one-tailed test. So when we go to a one-tailed test and 5 degrees of freedom, one tail, we're going to get 2.015. And then the t-test is going to equal the statistic, x bar. If you want to put d bar, you can do that, minus the mean or the mean of the differences if you want to do that, divided by sx bar, which is s divided by the square root of n. So we would have 3 minus 0 divided by 6.099 divided by the square root of 6. And that is equal to 1.205, just to carry it out a little bit further. And that is not, let's go down here, 2.015 is not greater, 1.205 is not greater than 2.015. So you fail to reject HO. Their mu could be 0. And of course, that fits with what we had said earlier. And then on the calculator, so we cover all the ground here, do stat, test, t-test. And make sure your mu 0 is 0 there. Still in list 3. And just go down and hit calculate. And I get a t-value of 1.205 about. You might note also that the p-value is large. It's greater than 0.05. So that also supports the idea of failing to reject HO. Okay, so problem 5, hopefully you can see that we're looking for a relationship and that we have 2 qualitative variables, at least one of which, in this case, both of which are multinomial variables. So this is a chi-square test, and we will, for HR, there is a relationship between anxiety level and the need to succeed in school. And not. So I am going to use my calculator on this one. I'm just going to go to the matrix and edit and put in a 3 by 3 matrix, and then just enter all of these numbers into the matrix. you can impose, I'm going right to this. And I hope you're back. Maybe you never left. I'm going to hit Stat, Tests, and then arrow up to chi-square test, and just go down and hit Calculate. And the p-value is 9.04 times 10 to the minus 6th. In other words, very small. We're going to reject HO if the p-value is less than 0.05. 0.000000904 is less than 0.05. So we reject HO. Conclude there is a relationship between, and I'm just going to, this. We've rejected HO, so there is a relationship. Okay, also you can see there, let's say if we had done this with the C critical value approach, we would reject HO if chi-square test is greater than some value, and our degrees of freedom is number of rows minus 1 times number of columns minus 1, 3 minus 1 times 3 minus 1, that's 4. So looking at the chi-square table, finding the chi-square table, it's in here somewhere. For alpha 05 and 4 degrees of freedom, that's 9.49. And then on the calculator, we found a chi-square test of 28.69, and that is greater than 9.49. So again, we reject HO and conclude there is a relationship. Let me erase all of this, and actually I want to write something up again here. Let me pause. Okay, this is just the same problem. This is going to be a little messy because the numbers don't, well, they're not as nicely done as I'd like for them to be if I were going to work this by hand, but that's life. What I'm going to do here is just show you how to go about working this problem and getting the chi-square test value by hand again. So the first thing to do is to sum all of the rows and then sum the observed frequencies in all of the columns. And get an overall total by, you can either sum all the numbers in the table or sum these, the 98, 112, and 36, or the 61, 127, and 58. In any event, you should end up with 246. And so what I'm going to do first is compute the expected values for each cell. And so in this cell, the expected value is equal to the row total, that's 98, times the column total, that's 61, divided by the overall total, that's 246. And that's about 24.3. And let me give you one more. I'm going to give you all the expected values, but let me do one more just where I calculate that out all the way together, all the way out like this, and show all of that. The expected value here would be the row total, 112, times the column total of 58, divided by the overall total of 246. That's about 26.4. And now I'm just going to write down the expected values, and the rest of these you can verify those if you'd like.